I'm going to talk about the specific portion of the project that I was tasked with, and that involved the modeling program INVEST, and so specifically water-related ecosystem services in our study area using INVEST. First off, I'm going to look at the context of our research, the why, the where, and briefly describe our scenarios, and quickly talk a little bit about how INVEST works, and then get to the results and the conclusions. Ecosystem services is defined as nature's benefits to humans, a very anthropomorphic idea, and in relation to water, we're talking about a clean, plentiful supply for now and for the future, and also what does nature do to reduce the social costs of things like flooding events, water quality issues, and so on. And so what factors are we looking at to understand how these ecosystem services might shift? And specifically, we're looking at changes in land cover based on urbanization and management practices along with climate. So with that in mind, we're going to test several scenarios using INVEST to see how these might change in the future. So here's our study area, but I want to also emphasize how much change is occurring in this area. The Tualatin Basin is roughly corresponds to Washington County, an area just west of here that's going to potentially see quite a bit more growth in population over the next several decades. And with that in mind, there's probably going to be a fair amount of urbanization in land cover as well. And so this graph here is just showing that Washington County is probably, besides Multnomah, the most urbanized area in the state, and it's going to continue to grow. And there's also other communities as well in the area that are going to probably have the same thing happen. So I just want to go over my modeling framework really quick. I helped develop the urbanization model, a very simple, somewhat simple GIS process that was informed by our stakeholder workshop. And it was very overwhelmingly decided that the regulatory framework in this area was going to be what drives urbanization. So we simply gathered spatial data on these regulations, specifically the UGB, that being the most important criteria that we used, added these all together in a weighted overlay, and subtracted out protected areas. And we have a graded map at the end from 1 to 9 that will guide where urban land cover will take the place of other land cover types. And so this is just a quick idea of what's going on here in terms of where land cover is possibly going to grow in the region. This happens to focus on the Hillsborough area west of here on the Sunset. And a lot of industry is potentially going to come in there, and we're going to see some growth. And we decided to use some simple metrics in terms of population growth rate, jobs per hectare, households per hectare, and come up with just a very rough sketch of how much additional land is going to potentially need to be urbanized to come up with these scenarios. And then our management assumption is very simple. We were just looking, especially in our area, where there's a lot of emphasis on restoration and what would happen if a lot of streams in our area had their riparian buffer zones restored. So we did a very simple, and it might be difficult to see on this map, but a very simple overlay of riparian vegetation in our study area along stream corridors. So going from this map to this map, you can sort of see those streams having additional vegetation placed on them. And then just to go over briefly about our climate scenarios, and as you can see, we're looking at typically winter precipitation increasing and decreasing in the summer, but that's reversed actually in the low scenario. So now I'm going to talk a little bit about INVEST. It's a GIS-based modeling tool. There's actually a suite of models that comes with INVEST. These are available for free. If you go to the Natural Capital Project's website, you can download it and try it yourself if you like. They have models for everything from coastal areas, marine areas, to several terrestrial ecosystem services, all ecosystem service-based. I focused on their 3 freshwater models, water yield, nutrient retention, and sediment retention. So these models are very simple in the 2 diagrams. They are showing kind of this conceptual framework, the conceptual approach that's taken with INVEST. And it's sort of a pixel-based approach, parcel-based approach, and there's very small amount of parameters to use. So the idea is that potentially this might be an easier modeling method to communicate with stakeholders and people who are managing ecosystem services. And quickly, we used several gauges in our study area to calibrate INVEST. And we had water yield, and then we also used concentration values from Clean Water Services, one of our partners, for those gauges to develop a load using the USGS LOTUS program. And just to present just a little bit of the results for water yield, we're having a pretty good relationship here. I just want to emphasize that this is actually a 30-year annual average, so we did a high level of aggregation on our data. INVEST works at the annual scale, and it's also suggested to average those annual values. So it's very, very coarse at a temporal scale. So these results are very preliminary, but one of the portion of our project is also to convey what we consider a fairly simple model and INVEST to a lot more complex process-based model, SWAT, Soil Water Assessment Tool. And these are some scatter plots. I hesitated to put the R-square on them because we're still working through this. But we seem to have a pretty good relationship with water yield so far. And we have some general relationship with nutrients, both phosphorus and nitrogen. And sediments, we still don't have any idea what's going on, but we're getting there. So we've actually made some progress on calibrating SWAT recently, so hopefully those results will change soon. So now I'm going to present to you a series of maps of our results aggregated to a sub-basin level, kind of analogous to a HUC 12, a hydrologic unit code 12, but these were actually delineated in SWAT. But on our x-axis here, we have our land cover. So the managed high actually represents a high urbanization scenario with those riparian buffers in place. And then on the y-axis, we have our climate models. So I'm a little more interested in showing you the spatial patterns and the kind of the broad relationships that are happening, and less so in the magnitudes. But this is our baseline, and these 3 here are the percent difference from baseline to the future scenario. So here's water yield, and as you can see, it's fairly heavily driven by climate. There's some subtle differences that are based on land cover, but more or less we're looking at a climate driven process, which is to be expected. So it turns out medium, which is the Meroc 5 model, is at least at this annual scale we're working at predicting higher water yield. And our high scenario is predicting across the board reductions. So climate change is the main driver there. Urbanization and the restoration impacts are a little more subtle. And so does the new land cover have more or less evapotranspiration potential So are we going from an agriculture to urban or a natural vegetation to urban? So that's what's actually affecting those values. So here we have total nitrogen results, and once again the baseline there on the left. And as you can see, this seems to be that this model is very land cover driven. So on our y-axis, we're not seeing a whole lot of differences, but on our x-axis we are, especially at the on the right side there. And also it appears as if we have a little bit of a difference between the two basins, where there is urbanization in the Tualatin. It seems to increase loadings, and in the Yamhill, so those brown patches in the middle there, sort of roughly corresponding to McMinnville, possibly growing, it actually reduces nitrogen. We're still not really sure what's going on there, but it just seems as if Yamhill has much higher loadings than Tualatin. There's a number of reasons that might be the case, and so we're still working that out. Phosphorus, similar results. INVEST is once again a very simple model. It's not necessarily capturing all the dynamics of nutrient cycling in the study area, so the processes are actually quite similar for the two, and we're getting very similar results. So here's sediment. This model seems to actually have a combination of effects from both land cover and climate. And once again, maybe this model actually uses the universal soil loss equation as its basis. So higher erosivity due to higher winter precipitation is probably driving this phenomena we're seeing. And once again, our riparian buffers are substantially decreasing from the baseline in most subbasins sediment exports. So that seems like a very positive result, but I think we need to maybe temper this by saying that INVEST is actually pretty simple in its approach, and maybe it's overemphasizing just one aspect of the landscape. So just to reiterate, it seems as if both land cover and climate are influencing erosion in the study area, and it projects increases, but that's mitigated by our sort of large-scale restoration buffer installation scenario. There's a lot of assumptions and limitations here. I'm just going to briefly go over them. And so we're projecting a long-term estimate based on highly aggregated data. So we're not really getting at seasonal effects or anything like that. So it's more or less just a long-term estimate. And and like I've mentioned before, these mechanisms are pretty simple for a variety of reasons, and they're not necessarily capturing some dynamics that might be influence the results. And so we don't necessarily, INVEST doesn't necessarily have a way of formalizing these the uncertainty in these estimates. So we're going to hopefully address that a little bit with a sensitivity analysis in the future. But we're considering, what a lot of people have mentioned already in their presentations, all the steps, all the uncertainty that's introduced at each step. This is a major problem still. So I think that's it. Just to briefly conclude, we do have these problems and limitations, but it's still spatially explicit. It's mappable, so we could show stakeholders where changes may occur potentially on the landscape. So that's a good thing. And once we model more of these, both freshwater and terrestrial, we could potentially bundle them together in an index and give people an idea of the distribution of all the ecosystem services on the landscape. And we can start looking at the different trade-offs and the consequences, both in economic terms and social terms.